Hello friends, I am Dr. Sirajul Faizi. I welcome you in my YouTube channel. Today in this video, I am going to talk about stereochemistry. Isomers are different compounds with the same molecular formula. You know that. You also know the two major classes of isomers are constitutional isomers and stereoisomers. Constitutional or structural isomers have different IUPAC name, the same or different functional groups, different physical properties, and different chemical properties. Stereoisomers differ only in the way the atoms are oriented in a space. They have identical IUPAC names except for the prefix like cis or trans. They always have the same functional groups. A particular three-dimensional arrangement is called a configurations. Stereoisomers differ in configurations. Now friend, a comparison of constitutional isomers and stereoisomers. You can see here 2-methyl pentane and 3-methyl pentane. IUPAC name different, same molecular formula, different name. Constitutional isomers. You can see cis 1,2-dimethyl cyclopentane and trans 1,2-dimethyl cyclopentane. Same molecular formula, same name except for the prefix stereoisomers. Now friend, isomers have two classifications, constitutional and stereo. Stereo have further classifications in like enantiomers and diastereomers, mirror image, non-mirror image, and then diastereomers again classified into two groups, configurational diastereomers and cis-trans diastereomers. Now friend, constitutional isomers. Constitutional isomers are isomers which have the same molecular formula but differ in the way that their atoms are connected. Butane chemical formula C4H10, 2-methylpropane chemical formula C4H10. So constitutional isomers: ethanol, dimethyl ether, 1-chlorobutane, 2-chlorobutane, pentane, isopentane, acetone, and propanaldehyde. Now friends, geometrical isomers. The pi bond is an alkene, does not permit rotation. Thus all of atoms attached directly to the alkene lie in a plane. Group attached to the alkene could be positions on the same side of the alkene or opposite side of alkene. Such compounds are different in chemical and physical properties as well as in their geometry and are called geometrical isomers. In 2-butene, the methyl group can be located on the same side or on the opposite side of double bond, giving rise to two geometrical isomers, cis-2-butene, trans-2-butene. The isomers with the group on the same side is called the cis isomers, while the isomers with the group located on the opposite sides is called the trans isomers. Trans isomers of compounds are usually more stable than cis isomers. Geometrical cis and trans isomers result from restriction rotation. Compound with double bonds, cis isomers have the same constituents on the same side of double bonds, Z, glutamine, together with the more complex molecules having high priority group on the same side. Trans isomers have the same substituents on the opposite side of the double bond, integer opposite, with more complex molecule having high priority groups on opposite side. Compounds with the bond in a ring. Cis isomers have the same substituents on the same side of the ring. Trans isomers have the same substituents on the opposite side of the ring. Now cis 1,2-dichloroethane, Z 1,2-dichloroethane, trans 1,2-dichloroethane, E 1,2-dichloroethane. Groups with higher priority on the same side, Z isomers. Group with higher priority on the opposite side, E isomers. If one of the two carbon atoms of the double bonds has two identical substituents, there are no trans-cis isomers of that molecules. You can see 1-pentene, 3-ethyl, 3-hexene, and 1,1-dichloroethene. Name the following geometrical isomers: trans 3,4-dichloro-3-heptene, cis 3,4-dimethyl-3-octene. You can see here. Now, cis-trans isomers are molecules having the same arrangement of atom but differ in spatial orientation of their substituents. You can see here the cis-1,2-dichlorocyclohexane and trans-1,2-dichlorocyclohexane. How this is the trans, this is the cis. See, cis and trans. Determine whether the following substituents cyclohexane are cis or trans isomers. Now friend, optical activity. Optical activity is the ability of chiral molecule to rotate the plane of polarized light, measured using polarimeter. Light that has been passed through a Nicol prism or other polarizing medium, so that all the vibrations are in the same plane, non-polarized and polarized. Polarimeter, an instrument used to measure optical activity. A simple polarimeter consists of a light source, polarizing lens, sample tube, and analyzing lens. You can see here in pictorial diagram light source, polarizers, sample tube, analyzer. Now friend, dextrorotatory, positive, an optically active compound that rotates plane polarized light in a clockwise directions. D. Do not confuse with capital D. Levorotatory, an optically active compound that rotates plane polarity in counterclockwise directions. L. Do not confuse with L. The angle of rotation of plane polarized light by an optically active substance is proportional to the number of atoms in the path of the light. D. Lactic acid and L-lactic acid. Now friend, specific rotations. The angle of rotation of plane polarized light by 1 gram per cubic centimeter sample in a 1 decimeter tube. Alpha D, D sodium lamp, lambda 589 mu. Alpha D is equal to alpha divided by L into D, where alpha observed rotation, L length decimeter, D concentration, G per cc. Alanine alpha D is equal to plus 8.5, lactic acid alpha D minus 3.8. Specific rotation depends on the nature of substance, wavelength of light used, concentrations of solutions, thickness of the layer, nature of the solvent, and temperature at which experiment is conducted. Asymmetric center. Chirality is not reserved just for object. Molecules can be chiral or chiral. Chiral molecules, generally molecules containing an asymmetric center. Asymmetric chiral center, tetrahedral atom bonded to 4 different groups indicate with a asterisk. You can see an asymmetric center. 4 octanol, 2 bromobutane, 2 4 dimethylhexanes. Chiral object, right hand, left hand, right ear, left ear, and further another example. Chiral objects are objects with left-handed and right-handed forms. Achiral objects that have superimposable mirror image. Non-superimposable mirror image, a mirror image that is not the same as the image itself. Chiral objects have non-superimposable mirror images. Now chiral center, a point in a molecule where 4 different groups are attached to carbon is called a chiral center. If 2 groups are the same, then there is only one way. A chiral molecule usually has at least one chiral center. Stereogenic center, you can see here. Stereogenic center, 3 bromohexane. This carbon is bonded to hydrogen bromine CH2CH3, CH2CH3, CH3. 2 different alkyl groups. 3 bromodecanes, substituents on carbon 5, you can see hydrogen bromine and 2 different alkyl groups. So label the stereogenic center in each molecule, decide if it's chiral. How many stereogenic center does each molecule have? Now you can see symmetrical plane, not symmetrical plane, symmetric plane, achiral, not symmetrical plane, chiral. Now configurations. The arrangement of atoms that characterize a particular stereoisomers is called its configurations. Following methods are used to assign configurations: A. Absolute configuration, RNS system; relative configuration, D and L system; Fisher projection and DL notation. The first system for doing this was developed by Fisher and Rozanov around 1900. Fisher first developed a method for drawing carbohydrates in 2 dimensions and a conventions with respect to orientation, so as to indicate their 3-dimensional structure, so-called Fisher projection. Fisher and Rozanov then devised notations for designing the configurations of Stereogenic Center, depicted in Fisher projections as either D or L. A symbol capital D and L do not relate to the sign of rotations of an optically active molecule, which is designated positive or negative element. Example: D plus glyceraldehyde was defined as being D because the OH groups attached to the C2 is the right hand side RHS of the molecule when drawn in its correct Fisher projections, in which the CHO groups appears at the top. In enantiomers, L-glyceraldehyde was defined as L because of OH group is on the left hand side LHS. Now in carbohydrates, in general, the OH groups attached to penultimate carbon atom in the chain determine the assignment of D or L. Thus, plus glucose has the D configurations and plus ribose and L configurations. The notation was extended to amino acid. L enantiomers are those in which the NH2 group is on the LHS, and Fisher projection in which the carboxyl groups appears at the top. Conversely, D enantiomers are those in which the NH2 group is on the RHS, thus positive alanine and negative serine are L amino acids. So you can see here L alanine and L serine, Fisher projections. Now friends, Kohn-Ingold-Pirolov sequence rule, RS notation system. Assigning the absolute configuration, use the Kohn-Ingold-Pirolov priority rule to assign priority 1 through 4 to the 4 groups on the chiral atom. Orient the molecule so that the lowest priority atom in the back away from you. Look at the remaining 3 groups of priority 1 to 3. If remaining 3 groups are arranged to the priorities 1 to 3 are in clockwise fashion, then assign the chiral center as R, rectus or right. If the remaining 3 groups are arranged 1 to 3 in anti-clockwise manner, then assign the chiral center as S, sinister or left. Kohn-Ingold-Pirolov CIP sequence rule number 1. The atom attached to chiral center with the highest atom number is equal to 1, next to it is. Sequence rule 2. If the 4 atoms attached to the chiral center are not all different, the sequence is determined at the first point of difference. Now friends, you can see here the orient lowest priority group away. This is 4 is the lowest priority. So this is the away, and then you can clockwise R. You can see OH and counterclockwise S. So reorient like this. Right turn R configurations. You can see rotate like this. S configuration, left turn. So you can see here RNS, R configuration and X configurations. Assigning priority to groups. This is important. Oxygen atom CH2OH 16. Carbon atom attached to carbon. Carbon from CH3 attached to hydrogen. Hydrogen is equal to. So some example group is order of priority highest to lowest. Highest, and this one is lowest. So assign some groups with double bonds. Now friends, for example, plus glyceraldehyde, the order of priority of the group is OH greater than CHO greater than CH2OH H, and configuration is R. Similarly, minus serine, the order of priority of the group NH2 CO2H CH2OH NH, the configuration is S. Now friends, in